Okay, welcome to the session today on computer vision. I'm Professor Bruce Thomas. I'm from the University of South Australia. We have 5 papers today. We have 2 conference papers and 3 journal papers. As with the other sessions, please enter your questions in the Discord, and we will circle through those questions at the end during the question and answer. So our first paper today is by Feng, University of Rochester.
Are you guys able to see the screen?
Yes.
Now it's in the present mode. Okay. So yeah, hi, my name is Feng. I'm 4th year PhD student from University of Rochester. And today it's my pleasure to present our work, real-time gaze tracking with event-driven eye segmentation. This is a joint work with Reality Labs research. As we know, AR/VR glasses could be next generation of wearable for everyone, and people can wear it all day long. However, the challenge here is a limited compute budget to support all applications. And our idea is to focus on the region of interest in the image, so that we can process next pixels and reduce the overall computation. In this talk, we are going to talk about how to apply this idea to gaze tracking. First, let me introduce the overall gaze tracking pipeline. So the algorithm will take grayscale image and feed into an eye segmentation stage. And this eye segmentation stage will classify each pixels into one of 4 classes. Then the segmentation result will be used in the gaze estimation stage to predict the gaze direction. The state of our pipeline will use DN-based algorithm in the eye segmentation stage. And those DN-based algorithm will take more than 85% of total execution time. So in this talk, we're going to focus on leveraging ROI in near eye images to accelerate eye segmentation stage. How to find the ROI is inspired by event camera. Conventionally, a frame-based camera will capture an object frame by frame at fixed time frequency. On the other hand, when an event camera captures the same object on the left, it will generate a sequence of events instead of images. That is because only the pixels with large color shifts will be activated. In this case, the region around black dot will activate events. So for near-eye imaging, events naturally become a sparse encoding of eye movements, since the background is most likely static. So our key insight here is that events naturally encode ROI information. With this key insight, we designed our event-driven ROI prediction network. Our network has 3 inputs: software emulate event maps, edge map, and ROI from the previous segmentation result. And we choose to emulate events instead of using actual event camera, so that no actual hardware is required to support our algorithm. Although event camera can operate at high speed, such as 10,000 Hertz, but such a high speed is typically an overkill for many consumer gaze tracking applications. Now, the event map is generated by subtracting the previous frame from the current frame and gone through an activation function that mimics the event camera. And edge map is generated by performing counting edge detection on the previous eye segmentation map. Both event map and edge map will be concatenated and used as input for the ROI prediction. To leverage our ROI prediction, we propose our multi-mode switching algorithm. Our mode switch module will use ROI prediction network to predict ROIs. In addition, the mode switch module can also select the execution path for the rest of the pipeline. In our case, we have 3 different paths. Both ROI prediction, ROI-based eye segmentation, and reuse will reduce the overall computation cost. And we only execute the full frame eye segmentation as a fallback option. Here's an example of executing our pipeline. So at time t0, our algorithm will always execute the full frame eye segmentation to get a segmentation result, because we don't have previous information to predict ROIs. And at time t1, we will emulate event camera in software and generate event map from the previous and current image. And this event map, along with the edge map, will be used in the mode switch module. And this mode switch module will predict ROI and use it to crop the full-size image. And the cropped ROI image then will be used in the ROI-based eye segmentation to get final segmentation results. So at time t2, again, we will generate event map and edge map, and these two will be used in the mode switch module. At this moment, because there's no event activities in the event map, so mode switch module will decide to reuse the previous result instead of operating the eye segmentation algorithm. This will further reduce the overall computation. So on top of acceleration from our multi-mode switching algorithm, we further accelerate eye segmentation stage by proposing a lightweight segmentation network. Similar to other segmentation network, we use an encoder-decoder architecture, but we use lightweight depth-wise separable convolution layers to reduce the overall computation cost and model weights. Here we show our model is order of magnitude smaller than the state of our algorithms. So in our experiment, we use OpenEDS 2020 for the evaluation. And in our evaluation, we have two variants. The first variant only uses ROI prediction with no reuse operation. And the second variant uses both ROI prediction and reuse operation. And we have three baselines, density.net, deep VLG, and RIT-net. Here's our results. So this is the evaluation on the overall gaze arrow. So the x-axis shows the normalized speed, and the y-axis shows its overall angular arrow. As we can see, our newly proposed eye segmentation network can achieve 2 times speed up with similar accuracy as other state of our algorithms. And by combining ROI prediction and reuse operation, our method can achieve up to 5.4 times speed up and retain the error rate within 1 degree. Similar result can be seen in eye segmentation evaluation. So our methods can keep high mean IOU accuracy with much higher speed up. Although there's a noticeable accuracy drop from our methods, this accuracy drop from the eye segmentation will not affect the gaze prediction accuracy. So in conclusion, we propose a novel ROI prediction algorithm that emulates an event camera and achieve precise ROI prediction in gaze tracking. And we also find out integrating ROI prediction in our algorithm can achieve significant speed up in gaze tracking without accuracy sacrifice. So this will be the first step to emulate event camera and accelerate AR applications. And we are hoping this idea can benefit other visual tasks and make all-day VR become a reality. So that's the end of my talk, and I'm happy to take any questions at the end of this session. Back to Professor Thomas.
Thank you very much. Very nice presentation. Our next paper is Yuichiro Fujimoto from the Nara Institute of Science and Technology.
Okay, thank you very much for the introduction. I will share my screen. Okay, so I'm Yuichiro Fujimoto of Nara Institute of Science and Technology in Japan. So today I would like to talk about structured light of flickering patterns having different frequencies for projector-event-camera systems. Oops. Okay, so this work was conducted by Yuichiro Fujimoto, Taishi Sawabe, Masayuki Kanbara, and Hirokazu Kato of Interactive Media Design Laboratory. So, okay, let's get started. So projector camera systems are also known programs and are widely used for 3D shape measurement and spatial augmented reality. However, conventional program is mostly used indoor with low lighting or outdoors at night, and is rarely applied in situations with strong ambient light. Of course, one of the reasons for this is that light can be observed more beautifully in a dark environment than in a bright environment. But another reason is that calibration and resolution issue between the projector and the camera, I think. In programs, the calibration pixel-based correspondence is often obtained by observing the structured light of the projector with the camera, and this becomes difficult due to the interference of ambient light. So we will focus on solving this problem. The purpose of this research is to propose a calibration method to construct a projector camera system that can work in a bright environment. The idea is to use an event camera, which has recently started to be used mainly in the computer vision field, As a normal camera observes the amount of light at each pixel, this camera detects the change of brightness at each pixel. So this information on brightness change is called an event. So as a simple observation example, here the cameras observe the high-speed rotating disk with a black circle. So I don't notice this is a really similar explanation as the first presenter's one. So in a normal frame-based camera, the black circle is observed frame by frame with severe motion blurs. However, with the event camera, we can observe them as a continuous dense trajectory like these figures. The event camera has a lot of merit compared with the conventional frame-based camera. The delay is very small because each pixel works independently. In addition, the dynamic range is really high, almost same as the human eye. It also has a contrast sensitivity, high contrast sensitivity in a bright environment. Sorry. So these features would be useful in solving the problem I mentioned earlier. So, but one of the problems in applying the event camera to program is that the conventional projector camera calibration cannot be applied directly. So in general, the pixel correspondence between the projector and the camera is first obtained by projecting a gray code pattern like these pictures and observing it with a camera. However, event cameras have limitations in terms of the number of observable events at once. In the case of gray code patterns, almost all pixels of the image changes at once, and it is difficult for the current event camera to stably detect all changes. So in fact, there are already several studies on active stereo with event cameras. The study on the left uses a motor-driven galvanometer and a laser beam for high-speed light scanning. This method is not intended for use with a standard projector. The study on the right uses a DLP module to project sinusoidal patterns. This uses a projector, but a coaxial frame-based camera is used for the calibration, which may not be available for all event cameras. In summary, as far as we know, the general purpose calibration technology between event cameras and projector is not yet established. In this study, we utilize the feature of event cameras on good at detecting brightness changes and propose a flashing pattern with different frequency for each row and column, like these videos. The event camera observes this flashing pattern and performing the frequency estimations to get correspondence with the projector image pixel. Here is the result of projecting and estimating 8 different frequencies using an ordinary 60 Hz 3 LCD projector. The color maps show the estimated frequencies, and you can see that the different frequency observed in each column and each row. The graph on the right shows the estimated result for each pixel on the vertical axis and the projected frequency on the horizontal axis. It shows 100% accuracy in this setting. As the 8 frequencies are insufficient to cover the resolution of the whole resolution of the projector, of course, we compensated for this by using a combination of 3 different patterns. So we compared the proposed method with a normal program with the frame camera and the gray code patterns. The first row shows the dark environment and the second row shows the bright environment. And the 2 figures on the right show the correspondences between the projector and the camera calculated by regular programs and proposed program. The white pixel indicate that the correspondence was found, while the black pixel indicate it was failed. In the dark environment, this is dark environment result, the correspondences of the entire calibration box is obtained in both programs. On the other hand, in a bright environment, a large part of the box is black in the normal program case. This means that the calibration was failed. However, with the proposed method, the correspondence is still obtained for the entire calibration box. So also the number is slightly reduced. So here is the result of the 3D shape measurement of the sphere. When the environment becomes brighter, this is a dark environment result, and this is bright environment result. And when the environment becomes brighter, the normal program produces a large missing lesions like this, but the proposed method does not produce such a fatal missing lesions. Okay, so this is the last slide. So as the next step, we are working on the high-speed 3D shape measurement. Thank you for your attention.
Thank you very much for an outstanding talk. Our next presentation is by Shaoyu Chen at the New York University.
Thanks for the introduction. Can you guys see my screen?
Yes, we can see your screen.
So hi everyone. Today I am going to present our work, Instant Reality, Gaze-Contingent Perceptual Optimization for 3D Virtual Reality Streaming. Nowadays, cloud-based streaming has widespread applications in music, video, gaming, and visualization. Traditional 2D video content streaming is typically designed for passive consumption, and thus latency is less an issue for most users. However, as shown in this video, the introduced latency from 2D streaming, like the huge and variable input lag, may cause delayed interaction or even simulated stillness. This can harm user experience, especially in highly interactive and latency-sensitive scenarios, such as professional gaming and virtual or augmented reality. In comparison, 3D assets can enable responsive interactions and collaborations. It also reduces the expensive remote rendering workload and saves network transmission with the reusable content. However, the video below shows the loading time of an example scene with 4 times playback speed. It still takes more than 20 seconds to load the whole scene. Therefore, even though realistic rendering can be achieved by modern processor technology, the required 3D assets could yet be handled by the existing network bandwidth. This can cause long latency that compromises user experience. To address this challenge, we present a gaze-contingent and perception-aware 3D immersive streaming system suitable for virtual reality application. The cloud uses individual user gaze information, so as the green dot here, to determine the perceptually optimal content sent to the edge. Our method can be applied to 3D assets such as meshes, volumes. It also works for dynamic scenes. Like full VAT rendering, we assign eccentricity importance based on to each pixel based on its distance to the gaze position. For example, if the user is looking at the hair of the leopard, the eccentricity importance here will look like this, with brighter color indicates higher importance. However, the abrupt change during LOD update may cause undesired popping artifacts and distract users. Therefore, we perform frequencies analysis on update to ensure temporal consistency. We evaluate the perceived change as a temporally adaptive variable contrast and use it as the temporal consistency importance. And this is a heat map given this LOD change, with darker color indicate better temporal consistency. Then, we combine the eccentricity and temporal consistency importance for each pixel, as shown here, and map it from 2D screen space to 3D units, which are triangle meshes in this example. The obtained importance of 3D units can be used as the priority for streaming and update the level like this. Our method also takes Sakar into account. It is known that Sakar can suppress the perception of the popping artifacts. For this reason, if Sakar is detected, we ignore the eccentricity importance and transfer the assets with most popping instead. We notice that the heavy frequency domain decomposition during temporal consistency calculation may result in intolerable latency and harm user experience. For this reason, we train a multi-layer perceptual neural network for fast prediction of the importance. With neural acceleration, Claudio can skip rendering the actual image when calculating the importance. The neural network is trained for a specific scene. It takes the camera position, camera direction, and gaze position as input, and output the predicted importance of each 3D unit in the scene on the given input. It can accelerate the computation from about 400 milliseconds to 20 milliseconds. We evaluated our method using 3 different ways: eye-track user study with VR headset, screen-based user study where user's gaze is fixed, and objective analysis. This is because of the limited access to participants during COVID. Our method is compared with method uniformly increasing the LOD of each unit based on visibility, and 480 streaming without considering dynamic consistency. We designed 2 tasks using 2 alternative forced choice experiments. Each trial consists of a pair of conditions among the 3 methods. The task 1 focuses on temporal consistency and was performed in both eye-track user study and screen-based user study. Task 2 focuses on the visual quality and was only performed in screen-based user study. Here are the user study results. For temporal consistency, our method was voted as significantly more preferred than eccentricity-based and uniform method, while eccentricity-based and uniform method have similar voting. Our and eccentricity-based method have similar visual quality, while both are much better than the uniform method. In objective analysis, we evaluate the visual quality using FOV video VDP. The gaze sequence are sampled from the eye-track user study. We measure the timing when FOV video VDP reaches a shared threshold. Our and eccentricity-based method have similar results, while both are significantly better than uniform method. We also analyze how bandwidth and latency affects the quality gain of our method by comparing the quality gain between our and uniform method of a single update. Our method shows significantly improved quality under all network conditions. In summary, our method delivers a statistically significant reduction of temporal artifacts without compromising the visual quality, and our method can work well under different network conditions. Thank you for listening.
Thank you for that excellent talk. I just remind all of our people who are in the room with us, please put your questions in the Discord for the end of the session. So our 4th paper, which is also a journal paper, is Juan Carlos de Bene from Stevens Institute of Technology.
Okay, thank you for the introduction. So I'll share screen. Okay, so can you see my slides? Okay. Okay, so I will present our work titled Prepare for Ludicrous Speed, Marker-Based Instantaneous Binocular Rolling Shoulder Localization. So the goal of our work is to estimate the absolute pose of a binocular camera system using only a single scan line from each camera. For this, we also use a special planar marker as the geometric reference. We'll show later why we use this marker. So our system has a few nice properties. By using only single scan lines, then the pose estimation frequency can now be orders of magnitude higher than the frame rate of the camera, because it will be limited by the frequency of the scan lines. And by using the planar marker, we obtain an absolute geometric reference, which allows our method to estimate the absolute pose without depending on previous estimations. And therefore, compared to previous methods, our method does not drift. So the planar marker is comprised of 5 lines in 3D space. And these are arranged in a way that it is possible to recover the observed 3 points solely from the image measurements. This is based on a well-known projective invariant known as the cross ratio. And the cross ratio is a number associated to 4 collinear points or 4 concurrent lines. And the intuition behind the pattern design is to define a map between the 3D points on the lines and the cross ratio values, as to be able to determine the 3D points solely from the cross ratios of the observed points in the image. So the reason we have to use two cameras is that our marker is planar. And then because of this, all the observations in a single scanline will be all collinear, which is a degenerate configuration for post-estimation. So by using a second camera, we are able to obtain an additional non-collinear point, which we can now use to determine the 6 degrees of freedom of the pose. So at this point, we could use the 2D tree correspondences to solve for the pose using any of the shelf generalized pose solver. But the problem is that these solvers usually require solving an octopolynomial, which is a very expensive operation. So we focus on leveraging the geometry of the marker in order to design a simple solver. So for this, we explore two geometric solvers, a minimal 6-point solver from 6 observations and a 10-point solver from 10 observations. One nice property of the marker we designed is that it is possible to recover the depth of the observed points in very simple closed forms, which is basically the foundation of the speed of our method, as we will show later. So at this point, we have to mention the assumptions our system makes. We assume that both scanlines were captured at the same time, that both cameras are calibrated, and that there is no radial distortion since we are using collinear measurements. And as for the minimal 6-point solver, we use the 5 points for the first camera and 1 point for the second camera in order to estimate the pose, but this still requires solving a degree of polynomial, so this was not a satisfactory result. Then we found out that by using the 5 points in each camera, we can directly determine the depths, and we can estimate the pose in a very simple closed form, which is with very few operations. So we have a very lightweight solver that gives exactly one solution. So as a final step, we consider a measurement refinement procedure in order to increase the accuracy of our methods in the presence of noise. So this poses a constraint optimization problem. The math and the details are in the paper. But one nice thing about this method is that it does not require information about the pose. So it is possible to perform as a pre-processing for the 2D image measurements. So the next step was to verify that our custom solvers were as good as any of the shelf pose estimator. And we found that, yes, it works quite nicely, but our 10-point solver is much simpler, which can lead to a very fast implementation. So we focus on the 10-point solver from here on. And next, our objective was to determine how sensitive our method is to motion blur. So we tested on synthetic images, and we found that, yes, it is quite sensitive to motion blur. So we have to be careful when selecting the exposure of the camera, how much brightness we want with the image, among other things. And after that, we moved on to evaluate our method with real data. So we use a binocular setup, which is close to rectify, which is a common configurations. We just have to be careful that the observed 3 points are not collinear, because again, that's a degenerate configuration. So we collected a small data set of real images. In this case, we use static images in order to be able to extract ground truth information using a standard P3P algorithm. After that, we also devised a method to be able to detect our pattern automatically in the images, by adding additional vertical lines, which provide additional truth ratios, which work as a signature of the marker in the images. And the purpose of all of this was to be able to build a hardware prototype of a pose tracker that can work at very high frequency with very low latency. And our hardware prototype can achieve a frequency of 129 kilohertz with only a 1 microsecond latency. So basically, we want to use this as a head pose tracker for a head-mounted display. So this was our prototype. So that's my presentation. Thank you for your attention.
That's fantastic work. I very much enjoyed that paper. So our final journal paper today is Huan Bao from State Key Laboratory. Oh no, sorry. That was the first author. No, Wei Wan Ji is the speaker. I apologize.
Hello, it's me.
Yes, yes. Sorry, I'm mispronouncing your name.
Okay. Let me share my screen. Can you see my screen? Can you see my slide?
Yes, we can see it.
Yes.
Okay. Hello, everyone. I will present a work titled Robust Tightly Coupled Visual-Inertial Odometry with Pre-built Maps in High Latency Situations. With the rise of the digital twin and high pressure maps, the demand for AR and VR of large scenes combined with high pressure maps gradually becomes prosperous. High pressure localization is fundamental to AR and VR. In general, there are several ways to obtain the device policy, such as GPS, VLO, and localization. VLO can output smooth trajectory in real time with high local accuracy. However, the cumulative drift in long distance tracking still exists. Compared with VLO, the localization algorithm has better global accuracy, requiring more computation. The motivation of our work is to fuse the pre-built map into the VLO tracking process to combine the advantage of VLO and the pre-built maps. We categorize these coupled methods into loosely coupled and tightly coupled methods. Without additional measurement to VLO, the loosely coupled methods can only continuously optimizing the Sixdorf transformation, leading to the jumpiness of the trajectory and the AI effect. Previous tightly coupled methods are sensitive to map noise and scenery changes. Moreover, the previous methods also lack the design to handle the localization with time delay and low frequency, which is not suitable for the application scenario of map services deployed on the remote server. We propose a novel molecular visual-inertial odometry system that utilizes low frequency global localization combined with pre-built maps. This system includes a complete scheme to generate the association between the pre-built map and the local features. We design different constraints for different types of map points. Besides, we also develop a degeneration state recovery strategy to recover the system from degeneration states. Inspired by technique widely used in dense mapping, we use recasting to obtain sparse point clouds from dense mesh. Compared with point clouds extracted by 2D and 3D matches, our method can get more clean and structured point clouds from the pre-built map. The descriptor of 3D point comes from the query image, making these points easy to check in the latest frame. The removal of outliers is the most critical step for a tightly coupled method. First, we project the map point into the latest frame for projection-based matching to build the correspondences of the map points and the local features. Second, we remove the outliers by checking the multi-frame projection error from each map point. Finally, we treat the remaining map points as a whole, and only when there are enough active map points, we will add them to VL optimization. As we believe the accuracy of global localization poses, we use projection cost for global map points. In contrast, we use co-planar cost for local map points, assuming local map points and their corresponding local features can be associated with the same plan. For degeneration state, we adopt the loosely coupled method to help recover the system to the tightly coupled state. We use post-graph optimization to optimize the drift between the pre-built maps and the VLO, and the initialization is a special case of degeneration. The VLO module needs to be initialized independently before using the constraints of pre-built maps. The experiments on neural datasets and the simulation datasets show that our method can achieve higher accuracy compared with the state of other methods. Compared with GMM and the DSL, our method is more robust to the changes of maps. Under the condition of high time delay and low localization frequency, our method can still achieve better accuracy than the traditional basic VLO. To better reflect the advantage of our method in practical application, we have implemented an AI demo that can run in real time on a mobile phone with the aid of visual localization on the remote server. The AI demo runs on a Huawei Mate 20 Pro. We reconstructed two open scenes, an indoor and an outdoor scene. The data were collected with a camera 5 months before the actual test. Therefore, both the environment and the device have changed significantly, which is a big challenge for the localization algorithm and coupled methods. For comparison, algorithm is deployed on the server. There is a network latency between 300 and 500 milliseconds per localization request. The localization interval is set to 1 second. Verify the drift accumulation through loop closure. The video shows that our method can output a much more accurate and smooth trajectory than the loosely coupled methods. That's all. Thank you for your time.
Thank you very much. And I would like to thank all the speakers. I will be honest, I am not a computer vision person, but I found this session extremely interesting. So thank you. So we'll go through the papers. We had a question for the first paper. For eye tracking, isn't the ORI more or less always the same because the eyes roughly remain in the same position relative to the camera? If so, why do you need an ORI prediction?
Actually, in eye tracking, most of the eye movement, they have cascade, and they have like a very subtle, like a very quick movements for eyes. So for eye tracking, we do need gaze estimation in order to, for instance, navigate like a UI interface, or for like Fourier rendering, those type of things. So like gaze tracking, you do need to predict the ROI, the range of interest.
Okay. We don't have a, let's see, question for the third paper yet, but I might have missed it, but how does the, what's the error between the traditional gray coding method and your new method? Is it, or do they perform about the same or different, or errors?
Sorry, are you asking the second presenters?
Yes, you. Yeah, sorry. Okay,
sorry, could you repeat your question again? Okay, you are asking a difference between, sorry.
Yeah, between the are both the traditional gray code method and your new method, do they have a similar accuracy, or are they different?
Right. Thank you for your questions. Yeah, actually, so we have shown the accuracy of the 3D measurement in our papers. So at least the accuracy of the pixel we can measure is almost same as the normal gray code patterns. But so the number of the pixel, we can get the correspondences between projector and the camera is higher than in our method than in the previous method.
Oh,
I mean the gray code patterns.
Okay, thank you. Thank you.
Thanks.
There was a question about the eye tracking, and then it was stated that they used the HCG Pro Eye that was a built-in tracker. But you have a follow-on question. How many participants did you have in your study when, because you said you was affected by COVID? Sorry, this is the third paper, Shaoyu Chen.
Okay, so for the eye tracks user study with the VR headset, we have like about 8 users. And
Okay.
for the screen-based user study, we have like 12 participants.
Okay.
But for each user, the study was repeated many times.
Okay, so probably no. That's amazingly good to do during COVID. We've had to run many studies, so it was difficult.
Yeah.
Okay, so for the fourth paper, for rolling shutter camera paper, what's the application of this work? Getting an HMD pose in an environment with a special geometric marker. I do a follow-on with that was, why do you require such a high or low latency with the tracking?
Okay, so why do we need high frequency and low latency?
No. So where could you use this, because you require these special markers? So what applications could you use this for?
Yeah. Right now the application, we are considered a control environment with the marker. We allow for this because we know that there are some customers that are willing to allow for fiducial markers in their environments. Okay.
Could you elaborate what sort of application domains these might be?
As for a particular application, our focus has been on just estimating the 6 degrees of freedom pose for a head-mounted display.
Could you speak a little slower? I didn't quite understand what you said.
Yes, our focus has been on being able to obtain the 6 degrees of freedom of the pose for a head-mounted display. That has been our focus. But as for a particular application, we don't have a focus right now.
Okay. Could you explain why you need this ultra high or low latency? Because the frame rate's only 90 frames per second.
In this case, our need for low latency is because by using low latency, we can obtain like a better virtual reality experience by being able to keep the virtual world matched to the moments of the user faster. So the user cannot perceive the difference between as the user moves, he cannot perceive the difference as the virtual world updates. This is the purpose of low latency. The high frequency pose estimation is in order to try to interface with some experimental high frequency displays, which can achieve up to 16,000 frames per second.
Amazing. Sorry, I'm like hardware. So for the last paper, can you compare against ORB SLAM 3? Also, is your code open source?
Yes, we compared the ORB3 and the ORB3 and we achieved a better accuracy than the ORB3. the post from Arabic 3 front end of Arabic 3.
Okay, is your code open sourced? Sorry.
Yeah. Huh?
And is that in the paper?
Sorry, I missed your sentence.
Sorry.
Can you repeat your?
Can people obtain your source code?
The source code of my work?
Yes.
Oh, no, not yet. Maybe someday in the future.
Okay, okay. Thank you. So please put your questions in the Discord. I have another question for the first paper. Does rapid eye movement affect the system? So if I'm moving my eye very quickly back and forth, does that affect the system?
So we actually evaluated on a very rapid eye movements data set. So in this data set, OpenEDS 2020, I think for in like 30 seconds video, it has like 8-7 on average cascade and also sub-random jump like eye blinks and also other eye movements. So I think the algorithm can adapt the like eye movements very quickly. And right now we're targeting for like 30 frames per second, but hopefully for like a much higher performance mobile device, we can achieve much higher frame rate.
Okay, good. For the second paper, when I looked at your paper, some of your experiments appeared to be done in very bright light. Could you explain what the luminance were? So could you explain this bright light scenario?
Okay, thank you for your questions. So for now, the maximum brightness we evaluated is 2,500 lux as a projection target. So this indicates our method works well in a very bright room, indoor room. But unfortunately, as you know, so the outdoor case, so the brightness would be much higher. For example, 10,000 lux in a cloudy case and 100,000 lux in a very bright outdoor. So it is very hard to apply our technique to this kind of situation. But so I think so the event camera is still under developing in terms of the hardwares. And so then we expect, so in the near future, we can very high contrast sensitivity event camera is available, I guess.
So what was the maximum lux that you could operate in?
For now, 2,500 lux as a projection surface brightness.
That's amazingly bright for indoors.
Yeah, that's as a indoors, very bright situations.
Okay, okay, no, very impressive. So Stephanie has a question for the last paper. Do you have any plans to create ground truth for the AR application in the future, or to evaluate this with users?
Sorry, I do not fetch your question. Can you repeat the question again?
Well, Stephanie is well, the second part, she's retyping her question, but the second part of it, do you plan to evaluate this with end users?
Yes. The demo is we will release in the future, and others can download download the apps or other approaches to get our demos and can get can use our demo in. Do you plan to release with and
so
to other users? Yeah.
I think the question is more along the lines of the accuracy of your system. Is the pose position accurate enough for people to use, to then use that to make AR applications? So, because all your descriptions were very large areas, so it's very difficult for us to see what the error is, because you know it's looked like the building you were walking in was tens, if not 100 meters long.
Yes, from the video we can see an AR demo which is recorded in real time that runs on a mobile phone. From the video we can see the AR effect is very stable, and both the AR effect and the trajectory is very smooth and stable.
Okay.
Yeah.
Okay. Okay. Just to follow on, I think it's quite difficult to evaluate this in an AR context. So I was just wondering if there is a good strategy to do that. I'm very interested to hear your thoughts about this. So you showed us a video of the arrows on the ground, but I think that is how much are, you know, can you put, so for argument's sake, can you put a box around a picture on the wall, or could you put a circle around a button, you know? So what sort of, how accurate can you make your AR annotations? And that determines how useful it is. It's very good work. It's not criticism of the work. It's just more is when you want to apply it to a real application.
Thank you.
Okay, I think we will move on. Question, paper number 4. I was wondering if you thought you could actually build this into a phone, or, you know, a very small, not you, because I remember it's a big engineering feat, but do you think this could get embedded into a phone or a head-mounted, you know, a self-contained head-mounted display?
Yes, I believe so. We will have to be careful with the configuration of the cameras to avoid seeing collinear points. And when it comes to this, the module used to estimate the pose, which is implemented in the hardware, well, in the FPGA, uses a very low amount of resources, so it should be feasible. But for future work, we're actually focusing on a single camera system, so that's where we're going right now.
Okay. Do we have any other questions? Paper number 3, Gaze. Could you elaborate on the types of applications that would use this? You showed some applications at the very beginning and then described the algorithm, but how would you see this work being applied in a real world application? Xiao or Chen?
Yeah, I think many apps can be benefit from this application if there is 3D access with level of details. For example, in the designer app, where the designer can fetch many 3D models from the cloud, and then they will copy reusing the content from the cloud. I think this is the typical example.
Okay, oh, good. Do we have any other questions? I have a final question for the last paper. What was the longest tracking? Because you had a very long route that you took that then reconnected at the end. What's the longest path that you've done for your tracking?
I don't remember the exact number. About I think it's fine to go about several hundred 1 kilometer. It depends on the prepared map you reconstructed before. It contains how large the scenery contains. Yeah.
Okay. Something about, oh, can you share your supplementary material here? Do you have a pointer to your supplementary material? Do you have a pointer to that? A link? Could you put that in the Discord?
Yes, we have. What was the longest? Can you share supplementary material? From the screen or in the website?
Could you put it in the Discord for people to look at now?
Yes. I will share open my supplementary materials.
Okay. Yeah, if you could put the link in, that would be great. Could we, because I think everybody they were taking pictures of all the sessions. Could everybody turn on their cameras?
This cut. Okay.
I don't know how to grab a picture. Are you putting your camera on? Way in?
Yeah.
Well, oh, I think we'll just, oh, there.
Okay. Can you see me?
Yep. Now I just have to figure out how to take a picture. Okay.
Oh.
Okay. I think I can do this. Okay. Thank you very much. Great talk, everybody. And I formally close this session. Thank you very much. There's 5 excellent papers. Thank you very much. Thank you very much, Mandy.
You're very welcome.
I don't need to do anything else, do I?
No, just log out.
Okay, thank you very much.
Yeah, see you.